Um, this week, going to do some further analysis on real transformers. Namely, we're going to look at how, in actual fact, the analysis of a real transformer for under load conditions, we can actually simplify our full model of a transformer quite considerably once we consider the transformer is loaded to any certain extent. And then we're going to look at how we can determine the values in that simplified model by for a practical transformer using what's called a closed circuit open circuit test to actually determine the values of the magnetizing reactance, the core resistor, and the component values representing the leakage flux and the copper losses. Okay, so that's what we're going to look at this week, and then we will either at the beginning next week, perhaps late on this week, take some open closed circuit readings from the transformer on the rig over there with a view to developing the modelling how that transformer should work with a particular load that we've also got on a rig, and then we'll connect that load up to the transformer on the rig and see if our model predictions were within suitable accuracy in terms of what we actually get in real life. So give that a try. So that's our complete model of a real transformer. We've got our two resistors R1 and R2 representing effectively the resistance of the windings, primary and secondary windings, and X1 and X2 representing the leakage reactances in the transformer, primary and secondary. And then we got our parallel components RC and XM representing the magnetizing, the magnetizing of the core and the core heating losses in terms of the open circuit transformer situation. But there is more detail than is really needed to solve most practical problems. I haven't looked at it, but I would think, you know, the effect of some of those components is likely to be much bigger if the reactive components are going to make a larger impedance if the frequency is much higher. So perhaps the frequency that's being used at could affect how much detail you need to include in your analysis. But I haven't looked at that side of it anyway, because we're talking about the high power mains system use of transformers here anyway. But we can simplify this and consider its action when the transformer doesn't have a load at all and when it's at full load. Okay, and in fact the simplified model is good for a wide range of loads up to the full load of the thing. So if we look at a real transformer without any load, okay, and we've already done this a little bit, with nothing connected to the secondary side here, there's no secondary current flowing. Okay, so I2 is 0, okay, because T1 is ideal, that effectively means this current at this point here, there's no current flowing out of the ideal transformer, there's no current flowing into it. You all agree with that? It doesn't mean there isn't a primary current, because in a real transformer there is. This means that the components R2 and X2, these two components here, have no effect when the transformer is open circuit, and we can ignore them. Also, the impedances of R1 and X1, these two here, are so small at open circuit that the volt drop across them is small, and they can be ignored in the open circuit situation. Yep. So the revised equivalent circuit for a real transformer at no load simply includes the components for the core heating loss and the magnetising current to magnetise the core. So that's a simplification of the transformer at no load, and essentially we really already have looked at that anyway, okay, but we're just clarifying that although we add these two components for on-load analysis, detailed on-load analysis, but they're so small that we can ignore them for off-load analysis. We can get the transformer ratio from the ratio of the voltages, the nominal ratio of the voltages, all the currents. So it's easy to get that even if it's not stated. That's what that bit down the bottom there is doing. So if we now consider the transformer at full load, primary current IP is at least 20 times bigger than the IO associated with the core losses. This means that in the on-load situation, we could ignore RM and XM essentially, because if the actual primary current flow is 20 times bigger than those, they'll have little effect on the accuracy of the analysis in this case. Okay. So the revised equivalent circuit for a real transformer at full load is that shown below, which has just got the components for the copper losses and the leakage flux in the primary and secondary. And it's accurate to use that model for transformers loaded down to as low as 10% of their maximum rated load, and it would still be accurate enough to give you a decent analysis of the situation. Okay, everyone happy with that? Further simplification of the circuit is achieved by, as we've done some examples, transferring the secondary impedances over to the primary. So we've had a go at this, and that simply means if we multiply the impedances in the secondary side by the transformer ratio squared, we can take the ideal transformer out of the circuit altogether, and we've got a simple series circuit of a transformer on load. What must be remembered is that these are the only terminals that you can connect to on the real transformer, the ones to the outside world. We cannot put any instrument anywhere within this circuit here, here and so on to measure those values. Okay, so removing them, moving them everything to the primary side and removing the ideal transformer further simplifies the circuit. Then we can combine the two resistances, the R1 and the A squared R2 and the X1 and the A2 squared X2 as well, into one single resistor and one single reactance. We keep the load separate because that's what we're going to be interested in terms of the current flow and when that's actually connected in the secondary side. But once we've reflected them across, we can bring together the two sets of values representing the leakage fluxes into 1. So I'm sure you'll all agree that that's a much simpler model than what we started with in the first place, and quite easy to analyse. Because if we want to know what this transformer is going to do, we're not interested in the separate volt drops really across the two leakage reactances and the copper losses. What we're interested in is what's going to happen overall with this transformer when I collect 200 volts to the primary and I've got this load connected to it. What current's going to flow in that load and what voltage is going to be across it. We ain't interested in the detail of what's going on inside. We're interested in what the overall result is. But we need the detail to be analysed to a certain extent. Okay, everyone happy with that? So, like anything else we've done on this unit up until now, the best way to get your head around that is to have a go at an example. So, for the transformer shown below, we've got 220 kVA as the nominal rating, or apparent power in and out. The nominal primary voltage is 11 kV. Nominal secondary is 400 kV. So this is a typical last line of the grid, 11 kV down to 400 volt three-phase transformer that you might have. Okay. Nominal secondary voltage is 400 volts, and then we got some values for some components. We're going to use the simplified model to find the open circuit primary current, the power loss in the core, and the reactive power used to magnetize the core. So that's the simplified model, taking away the components representing the copper losses and the leakage flux, because we're looking at an offload analysis here. So where do we start in finding the open circuit primary current? So you're going to find total impedance. How do we do that? If we add them together, what type of circuit would that suggest?
Well,
yeah, but combine them, yeah. So they're in parallel, Tom, aren't they? So we'd need to use probably the product over sum method here. So that'd be RC times XM over RC plus XM, wouldn't it? Yep. So we're talking about 27.5 27,500 times 16,500 all over 27,500. $10.3K. A useful check there is for parallel combinations, the total is always less than the smallest one component in that parallel combination. So we'd know we'd gone wrong somewhere if we got a total less than 16.5K. Right? So carry on and find the the current IO now. Heading down the wrong road here, because we've got a complex situation here. But it's not, the issue here is, it's not, we're not adding them together, that's adding them together. But we have got to take into consideration that they're not in phase with each other. Even though we're not adding them together, but we need to use their complex values. Yep. So we need to revisit this. So we've got to take into account here RC XM over RC plus XM. This is, if we do it in full on the top here, it is 27,500 angle 0 degrees times 16,500 angle, tell me, 90 degrees, yeah, all divided by, and what's that in, because we're going to add down the bottom, so we want them in rectangular form. What's that in rectangular form? Just 27,500. And this in rectangular form? 16,500J. So that's the arithmetic we've got to do. Yep. So a couple of 3 minutes to get me a result for total impedance, please. Right, what we got then? That's the final answer. What happened with that bit? Just to show, for the benefit of the video, we show the intermediate stages. What's the top two multiplied together? It's a big number, I know. We multiply these two, yeah, and add the angles. 27,500 times 16,500. Just multiply the magnitudes, add the angles. Right. I got 454 times 10 to the 6 to 3 significant figures. Yeah. Angle 90 degrees. Yeah. And then I converted the bottom to polar and got 32070 angle 31 degrees. Do you agree with that? And the result of that, what were you got to say it was, Matt? 14, so? Yeah, I got 142. 14.1k ohms, angle 59 degrees, twin friends. Yeah. Okay, so I agree with that. So that's our total impedance. Now we should be able to find from that, therefore, OC current IO is equal to, how do we find that? EP of ZT, yeah, simple Ohm's law. primary voltage is 11,000, isn't it? Angle 0 over 14,100, angle 59. Yeah. So we get 0.77 amps, angle minus 59 degrees. That's the open circuit current flowing. So, having found the open circuit primary current, how can we go about finding the power loss in the core? What method would you use? So we could use I squared R, but it's got to be I squared RC. Do we currently know just the current going through the resistor? No. We could calculate that, but is there another method? We could do P, or P is equal to, that'd have to be IR times RC. Again, do we know IR? No. Yeah? Yes, no? What's the third method for calculating power? Correct. We can use E squared over RC and look at the circuit. Both components are in parallel and they're both connected to the voltage EP. We got that there in front of our eyes. Take the easy route. Don't get caught out in the exam thinking, oh, I'm going to go and end up going a whole complicated way around it. It is 11,000 squared over the resistance R, 27,500 equals . $4,400 watts. Yep. So, the last part of the question asks you, what is the reactive power Q, that is, used to magnetise the core. So the reactive power Q is equal to E squared over xm (11,000 squared over 16,500) equals we don't worry about the 0.3, okay? 7,333 var. Okay? Here we don't need to worry about the angle because our voltage has got an angle of 0, and we'd expect this value's got an angle of 90 degrees. It's going to turn that into having an angle of 90 degrees. We know that already, that the Q is not angle 90 degrees. And when we've got per resistance, we don't have an angle associated with it anyway. Yep. So that gives us the in phase and out of phase components of S, which is the VA. So if you were asked to find the VA now, how would you find it? Yeah, we'd use, effectively, we'd add those two together using the power triangle P and Q, like so, and get S in there, if that was being asked for. Alright? And again, that current, what's the check I've said to you before with regard to that? What can we check that against? Whether that angle is what we would expect it to be. Inductive load, CIVIL, inductive load, current comes after the voltage, current's lagging the voltage, and it is. So you should, if you've got an inductive circuit, and that's overall inductive, there might be some capacitive parts to it, but if overall it's inductive, in this case we know it is, we got a lagging power factor or a lagging current, we know we got it right. Just worthwhile, because there was nearly a 59 degrees coming there right near the start, weren't there, Danny? Without the negative sign. And but that check would have shown that up. Okay? So use those little knowledge tools that you've got to check your results.